Hey guys, welcome back. So next up is the chain rule. So we're going to use this to pretty much deal with the derivative of a composition function. So remember, a composition function is one where you have like f of g of x. And how this derivative of something like that will play out. So the idea is, so we have f of x is defined as g of h of x. Again, both these functions are differentiable. H of x is differentiable function defined as u. And then g of u is another differentiable function now of that same variable. So we can go through this formula right here. So f of x is g of h of x. What we do is take the derivative. We take the derivative of g at the original h of x and then times the derivative of h of x. So more often than not, because it's talking about a composition, we're talking about an expression being raised to a power. That's a very common application of the chain of effects. The only application right now with our polynomial-based functions. When we get into the non-polynomials, then the chain rule applies to anything that's not just simply like sine of x is just a simple polynomial trig function, but sine of x cubed would be a chain rule application. We'll get into all that again in Unit 3. So right now we're just dealing with expressions being raised to powers if I'm giving you an actual function. So like right here, f of x is negative 3x to the fifth plus 5 to the fifth power. So the way the derivative is going to work is we're going to pretend that this is really like if we had x to the fifth power, instead of being the expression of the fifth, it was just x to the fifth, we would say 5x to the fourth. So that's what we do here. That's what f prime is. F prime is going to be a 5 in front. We leave the inside alone, and the exponent becomes to the fourth power. But because the inside is not just simply x, it has its own derivative, we have to now then take the derivative of the inside. So the derivative of the inside would be a negative 15x to the fourth. And this is where the name chain rule kind of gets its name from. Because depending upon the complexity level of the question, you could have a chain of derivatives that kind of stretches out for a little bit, especially when we get into some of the trig functions. That gets a little more complicated there. So you have the original derivative, which is based on just the power, the 5 going in front, the exponent decreasing by 4, but the inside not changing, and then we multiply by the derivative of the inside. And then we're going to clean it up a little bit. We're going to do that 5 times the negative 15x to the fourth, make it negative 75x to the fourth, and then negative 3x to the fifth plus 5 to the fourth power on the inside. We are certainly not doing anything else with that. If it wasn't being raised to a power anymore, let's say it started off being the expression was squared and we took our derivative, we could then kind of distribute inside. But since it's being raised to a power, that requires, like, again, your Pascal's triangle binomial theorem, which makes it far more complicated. And again, we're just leaving it the way it is. So it could be a situation where it's raised to a power like this, or it could be a radical. We have to recognize the exponent for radicals. So this would be negative 2x cubed minus 5 to the 1/2 power. So again, like our power rule, when we had the square root of x, which became x to the 1/2, and then became 1/2 x to the negative 1/2, same idea. Our derivative, the exponent goes in front, we leave the inside alone, and then we decrease the exponent by 1, which is a negative 1/2 power. And then now we multiply by the derivative of the inside. Derivative of negative 2x cubed minus 5 is negative 6x squared. When we multiply that by 1/2, we get a negative 3x squared, and then the negative 2x cubed minus 5 to the negative 1/2 power. Again, negative exponent, you are welcome to rewrite it into the denominator and then back as a square root. We wouldn't worry about trying to rationalize something like that. We would just kind of leave that part alone. And we just have negative 3x squared, and then the square root of negative 2x cubed minus 5 would be putting it into its radical format and getting rid of a negative exponent. Not necessary, but something you could, again, ultimately do. All right, so then like with our regular power rule, like with our regular product and quotient rules, we also could work with the table of values. So this is where it's going to pretty much be a direct application of the actual chain rule. So if h of x is f of g of x, our h prime will be f prime of g of x times g prime. Remember, the inside doesn't change, but we do have to account for its derivative. So h prime at 2 would be f prime at g of 2 times g prime at 2. So g of 2 is, in this case, 2. And then g prime of 2 would be 1. So now we've done g of 2, now we're going to do f of 2. So f of 2 is 1. 1 times 1 is just going to give us a 1. So we do need to make sure we are careful when we're trying to like evaluate out these different questions here in terms of like the order it's going to happen in or anything else like that. So just make sure you're careful with that process. Like for example, if I change this around a little bit, we're just going to change the table. Let's see, instead of this being a 2 right here, let's say this was a 3. So now when we do our h prime of x is our f prime g of x times g prime of x, we would get f prime at g of 2, g prime at 2, g of 2 is 3, so then f prime at 3 is going to be 2 there, and we're going to get 2 for that answer. All right, so just have to be very careful when using your table and evaluating out the process. All right, so that's our chain rule. We'll do a lot more examples of the chain rule once we get into the non-polynomial derivatives, because that's what it's entirely, it needs the chain rule there. That's another reason why we're kind of waiting until we get to that stuff before we worry about our non-polynomials. All right, so we do have a couple more things. We have what's called implicit differentiation, because everything we've been doing so far has been functions, but not every equation is a function. If you remember back to your conic equations, your circles, your ellipses, your hyperbolas were not necessarily functions. So getting into stuff like that, how do we take those derivatives? That's what we'll talk about there. And also the concept is, so everything we've been doing has been what's called the first derivative. We can do more. If I can take one derivative, why can't I take the second and the third and the fourth and so on? So those are our last two topics in Unit 2. So we'll get into those next. As always, appreciate everyone watching, and I'll see you next time.